So we're in the last topic of chapter 15, which is still still the second law of thermodynamics, but actually the last new quantity we're going to introduce, and that's entropy. So we have the conceptual pieces of the second law of thermo down, and it turns out that there's more than just a yes or no question that you can ask and answer about this. There's actually a number that you can put on the degree to which something is reversible or irreversible, and in a sense, time zero. So what we know so far is that some things just will never happen. So here are two blocks. I've got a hot block and a cold block, and I put them together so that they're able to have heat exchange, heat flow, and after some time later, they're both going to be warm blocks. So arrow of time, totally okay to flow that way. You would never expect to see this. So this is what the second law of thermo that we've at least described it as the Carnot version says this, is that you'll never have things spontaneously unequilibriate. So you could look at that in a mechanical context as well, and this is a little bit more elucidating, I think. So think about maybe Joule's experiment where he dropped these two masses, and the two masses spun this paddle wheel, which was set up to be kind of inefficient, and then it churned up the water, and he measured the temperature increase in the water. So in this case, this would be slightly colder than this. And he figured out exactly how much energy went into it, and therefore the specific heat of water. So again, time zero goes this way, totally fine. You would never expect to be looking at an unwound Joule apparatus, and then right before your eyes, the water starts unchurning the paddles and lifts the weights up out of this thing. Right? So time zero, again, only goes in this direction, not that one. And then finally, you can imagine this scenario where I have a whole bunch of particles that I've put through a velocity selector, either one of the mechanical ones that we kind of hinted about in lecture, or a velocity selector based on some of the diffusion principles that you investigated in one of the mini projects. So I just have a whole bunch of particles, and they're all speed v. So give me that. It's not impossible. And then I let them sit there for a while, and I will end up with, after they achieve thermal equilibrium, I'll end up with a Maxwell distribution of speeds. So they'll all bump into each other and turn into the Maxwell distribution. I would never expect them to do this, to start with the Maxwell distribution and then bump into each other and all end up in one exact same velocity state. So the thing that all of these have in common are that they actually don't violate the backwards arrows that I've crossed out. None of these violate the laws of mechanics. So it's totally mechanically okay to think about undoing all of the collisions that got you from there to there, or got you from there to there, or got you from there to there. Just play that movie backwards. Mechanics works the same forwards and backwards. But all of these we know just don't happen. So there's a concept called reversible and irreversibility. So these are all irreversible processes. There are, in thermodynamics as well as mechanics, all mechanical processes are reversible if you look at Newton's second law. There are reversible processes in thermodynamics, and the difference in between them is that in irreversible processes, randomness or disorder increases. Hard to see here, easier to envision here. The molecules in the water are more jiggly. Really easy to visualize here is that all of the particles, no matter which one I grab, it has the same speed. Whereas here, I can pick a random particle, and I have no idea what speed it's going to be. So in some sense, the disorder of randomness is manifest here. And in the end of the 19th century, people started to codify this. I think it was Clausius, who's responsible for one of our statements of the second law of thermodynamics. And he came up with an idea of a concept called entropy, which actually has a mathematical description. And this turns out to be a measurement of the disorder randomness. And so we can talk about reversible or irreversible in terms of whether or not entropy is zero over that change. So there is a quantitative measure of this. And my suspicion is he first noticed this in the context of the Carnot cycle, which is kind of what we'll end with. Remember that all Q's are deltas, so all heat flows are a change in heat. So this is the definition of this variable called entropy. So technically this is an entropy change. And it's defined as the amount of heat flow as temperature changes. And that might seem like kind of obscure. And we'll unravel a little bit of it. But first, just a couple of examples to explain what this thing is and why it actually manifests itself as a measure of disorder. So first thing, every time you see a new thing in physics, you got to put the units on it. You'll be kind of pleasantly surprised at the units of entropy because you've seen them before. So if I have heat over temperature, then I have our old friend, joules per Kelvin in SI. Right, so this is the same units as the Boltzmann constant as well, which we ran into before. And my advice, I don't know, so people still argue about how to explain entropy. I'll give you like a hint at all of the ways that people explain entropy. But to be honest, the best thing to do is just calculate it a bunch, make sure you understand how to calculate it, and know this. So this is the fundamental and most important thing, is that if entropy change is 0 for a process, you can reverse it. And secondly, there's a phrasing of the law of second law of thermodynamics, in my opinion, the best way of phrasing it, that is a law of physics as deep as Newton's second law. So if you violate entropy conservation or entropy convexity, you're in trouble. So first, let's just calculate something. Okay, so conceptually, I have a kilogram of 0-degree ice. I'm going to melt it into 0-degree water. Does entropy increase or decrease? Exactly right, it increases. Okay. And let's calculate as needed. So that would be the heat flowing in at the particular temperature. Sorry, I put a delta on here that I shouldn't have. So I think I was saying delta Q, it's always delta Q, and then my hand slipped. So this is delta Q always over T. So the heat flow in at that particular temperature. So how much heat does it take to melt a kilogram of ice? Well, that's just the latent heat of fusion times the mass. And then what does that occur at? 0 degrees. This isn't a delta, so, which is why I realized that goof. This has to be in Kelvin. So this would be 273.15. So that's 333, et cetera, kilojoules per kilogram. We have 1 kilogram of ice, and this occurs at 273.15. Got to be Kelvin, there's no delta there. Okay, so the entropy increase that we get is 1,220 joules per Kelvin. And the important part is positive, and the important part is that in some sense what this is measuring is it puts a number on disorder. So if you take a real course in statistical mechanics, you'll figure out a lot more of what this means. Is it basically measures the amount of states that you can access. So I'll really quickly sketch that idea with a teeny tiny example. So let's say that we're at absolute 0. And let's look at a distribution like this. Well, at absolute zero, there's no molecular jiggling whatsoever. So every single particle is at 0 meters per second at absolute zero. This is the most ordered state that you can possibly have, right? If I put even the smallest amount of energy in, so let me just grab one of these particles and give it one little bump. And that would be, slightly greater than zero. You could think about it as maybe like, if you're familiar with the terminology of calculus, we'll call it epsilon, like the smallest amount possible, is that I can actually quantify in terms of energy and temperature. So I put in some energy and I could find the energy of that particular particle, 1/2 mv squared, kinetic energy, and relate it to the temperature. So in some sense, that's what this is measuring. Like, the amount of disorder and temperature I get for putting a little bit of energy in. But again, the true mysteries of entropy we'll gloss over. We'll just teach you how to use it to work in the patent office really quickly. So that is this. This is, again, the best version of the second law of thermodynamics. And it really is the same thing that we've discussed before. It's just in slightly different language. So environment means thing that you're not keeping track of explicitly, you don't care about, but is still sealed. So let's say that, for instance, I have a big sealed off chamber, and I put some like thermodynamic doohickeys inside of it, like some of these cubes that might be equilibrating through, random thermodynamic processes. Maybe they're in contact with each other, who cares? So this might be my system. And the sealed adiabatic, no heat flowing chamber, this might be the environment. Okay. We'll quickly get less abstract than that and talk about things like power plants, for instance, as the environment. And you can actually be more specific. So cannot decrease means it can never be negative. So we actually have two options. We can have delta S total, which would be the change in entropy of both the system and the environment. And we could have one thing happen. It could be positive. This would be an irreversible process. So this is the thing that those first three examples that we started talking about have in common. The two blocks coming to equilibrium, the Joule experiment that won't wind itself back up but will wind down, and the particles that are all at the same speed and through collision spread themselves out into the Maxwell distribution. They're all irreversible. And if I were to, some of the things we have the ability to calculate, some of the things not so much, if I were to calculate their total entropy change, the system plus the environment they're surrounded by, it would always be positive. So those are irreversible processes. We've talked about one. We haven't identified it explicitly as such yet. There are systems where the total entropy, system plus environment, is 0. And of course, this should be like joules per Kelvin, joules per Kelvin. These are reversible processes. So this is totally okay to run the clock backwards on. And there are things in the universe that do that. So if I have just two balls bouncing into each other, and I tried to look at the thermodynamics of that system, that would be reversible. And in some sense, I would calculate the entropy, and I could never get it not to be greater than 0 during the process. So this is what Clausius set out to do. He can put a number on whether or not things are reversible and how irreversible they are in some sense. And we're not quite done with that yet, so we're going to go to the patent office for a second. And let's say that somebody comes to you with a design for a refrigerator. And all of the other details of the refrigerator check out. It conserves energy, but it makes the following claim. So is this okay? Maybe. So the thing that I'm assuming is that all the other details check out. So technically when you freeze ice, it's withdrawing heat, so we really don't have any energy concerns per se. This is all right. We're going to be losing energy coming off of this. So you can imagine this twisted world in which the energy leaving the ice as it cools down powers the thing itself. So the issue with this is the following, is that we know from the thing I just erased is that the change in entropy of the ice is minus 1220 joules per Kelvin. So when we melted 1 kilogram of ice, we increased its disorder by positive this amount. If we're going to go from water to ice, 1 kilogram again, we've got to, essentially we're increasing its order, decreasing its entropy by this amount. So the question is this okay? So this is what we're doing to the environment. We're withdrawing 300 kilojoules from the environment. And we're doing that at 300 Kelvin. Isn't life great? So we have 1,000 joules per Kelvin. And when we add them up, womp womp, sad trombone, we have a negative total entropy change. So this whole process, we've basically increased the total order of the universe, system plus environment. That's really sad, despite what like your parents told you. You can't leave the world better off than you found it. Like entropy must increase. So this is actually not an acceptable. So you would reject it at the patent office, saying like you can't do that, regardless of how the energy actually works out. So really quickly, and we'll do basically just problem solving with this. First time you see entropy, and the second time you see entropy, and the third time you see entropy, it honestly won't make a ton of sense. And then one day you're calculating your 50th entropy problem, and it kind of starts making sense. I will really quickly go through 2 examples of how this might be used, and actually where this came from. So this is my suspicion. I haven't read the personal letters of Clausius, but I think this is where he came up with this measurement in the first place. So remember some facts about the Carnot cycle, is that the efficiency of the Carnot cycle is the maximum efficiency. And that's 1 over Tc minus Th. So the claim, and this really is the second law of thermodynamics too, the claim is that you can't get better than this. And the second thing we know about the Carnot cycle is that it's reversible. And now I'm going to prove it. So prove-ish it. So this is the Carnot cycle, and we operate along two adiabats and two isotherms on a PV diagram. So here's an isotherm, that's TH, that's TC. And here are two adiabats. And adiabats have the property that they have no heat flow along them. So let me just keep the same numbering here. I'll do A, B, C, and D. Great. Very creative. Okay, so here's point A, point B, point C, point D. So what I know about the isotherms is that there's no internal energy change. So from A to B, that's an isotherm. And what's true is delta U is 0. And by the first law, that's Q minus W, so that's QAB equals WAB. And that's definitely something. There's definitely some area under that curve. From B to C, that's an adiabat. And an adiabat is defined as Q equals 0. So the part that we care about now is that if Q equals 0 along that process, I don't care what temperature it is or if it changes, which it does, this tells me that delta S is 0. And just in case we need it, that would mean the internal change in energy in the gas is also equal to the work from B to C. But maybe we don't need that. And then likewise, from C to D, we have another isotherm. And so we can kind of ... QCD equals WCD. And then from D to A, we have another adiabat. Which tells us that the entropy change is 0, because there's no heat flow. No heat means no entropy. And here we have delta U equals work dA. We don't need this for this particular calculation, but I'm just reminding you because this is all kind of new stuff. Okay, so what? Well, let's calculate the total entropy change in this. Okay, so two of these we got 0 along the adiabats from B to C and D to A. That's 0 joules per Kelvin. So we really just have A and B, and so that would be QAB over TA, the top one, and then QCD over TC, the bottom one, I guess. We'll just call it that. Okay, we have already proven this, so, or at least postulated this. So this was when we first talked about the Carnot cycle, this is really just the definition of efficiency in general. This is QC over QH. So I should probably keep that same. No, I'll keep. AB is hot. That's cold. So sorry for the repeated C index. Is that these up to a SIGN sign are equivalent to each other. So the ratio of Q's is equal to the ratios of T. So the only thing that's left is one of these guys picks up a minus sign. So one of these picks up a minus sign. That's this one. So heat is flowing out from here to here. Temperature is decreasing. Heat is flowing in here. So QCD is the opposite of, in sign of QAB. And in fact, what this is TH over TH plus negative TC over TC, which is equal to 0 as claimed. So again, the ratio of heats being equal to the ratio of temperatures we're taking as an article of faith. You do have to say it's an ideal gas and work for that a little bit. But this is I think inspiration for Clausius is that this is a claim that this cycle is reversible. And because it's reversible, you can prove that it's the maximum efficiency cycle. And then finally, we'll do one more calculation of a realistic thing. Because at this point, we have all of these little pieces of how to deal with energy and entropy. So we can also rephrase the first law in terms of entropy. And what we had is the change in internal energy of the gas is Q minus W, so that's the heat flow into the gas, and that's the work done by the gas, which is why that kind of squirrely minus sign is there. I will call this T delta S for reasons that you'll see in a second, and I'll call this P delta V for reasons you already understand why. So this is the phrasing of work done in terms of thermodynamic variables. So imagine that I have a container, again, with a piston. Probably the last time I draw the container with the piston in this class. And I compress it under pressure by some delta V. That is the work. Okay. So I'm going to do this, and then you're going to see why for a second. So let's take a machine. And maybe think about this as the piston of a car engine, if that's helpful. This is just a long-form way of saying I'm keeping it at the same temperature. So temperature is associated with internal energy. Okay. So this is, in some sense, why the first and second laws are distinct, or an example of this. I've got something that's trapped inside of an adiabatic, or trapped inside of a container. I don't let the temperature change, so the internal energy, like same moles of gas, same temperature, so the internal energy is the same. But this might be a reversible process, or it might not. So it turns out it's, not to ruin the suspense, it's not going to be a reversible process, despite the fact that I didn't, in some sense, throw away, add, or subtract any energy to it. So whatever I'm doing to expand this, I'm never going to see it spontaneously reverse, is what this is saying. Okay, so this is first law of thermodynamics. It's just phrased in a way that gets me what I want, namely the entropy. And I know that that's fixed, whatever it is. Namely, it's fixed at 20 degrees Celsius. Okay, I didn't change the temperature. That means that the internal energy doesn't change, stated explicitly, just to be nice. All this is happening specifically at 20 degrees C. I can't use Celsius because there's no delta T there. It's just T. So that's 293.15 K. The entropy change is what I want. And then P delta V, 1 ATM is this many joules, or pascals, sorry. I want to be in SI units, and then delta V is 2 liters, or 2 times 10 to the minus 3 meters cubed. Okay, and then math happens. This is joules. This is joules per Kelvin. So this process is irreversible. We would never expect our constant temperature expansion of this gas to like spontaneously reverse itself. So again, we'll just do a couple of problems. We'll go through and classify a bunch of engines in terms of whether or not they obey the first and second law of thermodynamics. And hopefully at some point in the next 10 years, you just wake up in like kind of a feverish sweat and be like, oh, I finally get entropy.